Okay there. Hello, good afternoon. My name is Lucio San Pedro, and I'm going to be speaking on behalf of team number one, which includes Ana Maria Esquivel, Perla Grijalva, Emma Gutierrez, and myself. I'm going to be presenting the project Biomechanics Analysis, Cycling, and I'm going to be using this Word document to show the report and also the Excel worksheet to show the graphs and the tables done previously to obtain the results for this project. So first of all, the main reason we started this project was to highlight the technique carried out by a professional cyclist. Obviously, some biomechanical observations were taken in the pedaling of the cyclist, and using Richmond's project. I'm sorry. Using the Richmond's program, we could we were able. I'm sorry. We were able to place some markers in the joints of interest, which in this case are the hip, the knee, and the ankle. So once we obtain the coordinates, which are these ones, this for the hip, the knee, and the ankle, yes, to use the time as an important parameter, we placed markers every 5 frames until a complete cycle was achieved. Once this was completed in frame number 35, we used time as a parameter with 30 frames per second, which gave us a total of 0.0333 seconds per frame, meaning that the rate and time every 5 frames would be equal to 0.1666 seconds, as shown in this table and also the table here, where we have frames, times, and the coordinates for the respective joints, using colors as a visual aid. So with this, we proceeded to obtain the segments. Sorry, let me change the color of this so the numbers can be seen better. Let's see if, okay, there you go. So we have 3 segments: the segment HK, which is going to be the segment from the hip to the knee. We have the segment KA, which is going to be the segment from the knee to the ankle, and we have the segment AH, which is going to be the segment from the ankle to the hip. So to gain these measures, we had to do a little subtraction between the point where it starts to the point where it ends here. So in the segment HK, we used hip and knee, and X is going to be, for example, in this occasion, we're going to a knee, so this minus this, and we have the formula shown here, respecting the cell where it's the magnitude. Okay, we also did that for the Y, and here it is. And we're using the Pythagoras theorem, we obtained the radius of that circumference, which was the segment, right? So that way we did it like for segment KA, which is going to be X for ankle and knee, and then the segment AH, which is going to be X for hip and ankle, and every cell has its respecting formula here. Okay, later on we obtain the angles HKA and angle HK, and the horizontal. To obtain this, we used the law of cosines. Since these segments form a triangle, and we were sure it was not going to be a rectangular triangle, we proceeded to use the law we proceeded to use the law of cosines to obtain the angle in radians. However, since the angle was the thing that we were looking for and what we had were all the sides, we proceeded to let me show you. We proceeded to solve for the angle, and we use, let me show you, we use this formula here, which the angle theta is going to be to the arc cosine of the segment over the in x over the segment. I'm sorry, forget that. We use this one. A little technical mistake. We use this one. The angle C is going to be the arc cosine of a squared plus b squared minus c squared over 2ab. That's the formula we use to obtain the angle. Not this one. This one. So heading back to the worksheet. That way we obtained the angle in radians, and applying a formula function of the worksheet, we obtained the same angle but in decrease. So this is the angle that's between the hip knee segment and the knee ankle segment. This one over here is the one from the hip to the horizontal plane, and the way we did it was using the arc cosine of the segment HK. For example, in here, this is the formula we used, the one that I presented earlier. This one is the one we use. The angle theta is the arc cosine of the segment HKX over HK to obtain the angles in radian, and apply the same function to it to obtain it in degrees. Okay, later on we proceeded to look for these values of the tangential velocity, and for that we used several formulas. Let me show you. Okay. There you go. So this is the formula we used, and this one is the formula we used, but this one was the one we implemented in the worksheet. Yes, the changing in the angle over the time times the radius. As you can see here, let me show you here. So this is going to be this in radians. I'm sorry, this one, because it's for the hip. So we used this. It's going to be this minus this multiplied by the time. Oh, I'm sorry, multiplied by the multiplied by the segment, which is going to be J4. This one divided by the time, or the change in time, which is this one. The same thing we did for the velocity in the knee and the velocity in the ankle. There was just a little variation for the ankle. We used a different formula. The formula we used was the multiplication between L15. Okay. Yes, the multiplication between the angle. Yes, the angle times the radius to obtain the arc length. The angle times the radius gives the arc length. and that divided by the time, or the change in time, we are able to obtain the velocity, or the tangential velocity in this case, for the angle. Since the displacement of the ankle is proportional to the one in the knee, we use the angles for the knee instead of having another additional operation, right? And for the acceleration, well, we just applied the difference in the change in velocity over the change in time, which is this graph. This table over here is in function of this one over these ones. Finally, we proceeded to obtain the angular velocity and the angular acceleration. This what we did was the change in, here we go, okay, the change in the angle over the time, which is this one, and this one was the change in velocity, angular velocity over time. Piece of cake. So we have the graphs here for the segment length according position, the position of every joint in X, and also a position for every joint in Y. Over here we have, in function of time, which is constant, we have the tangential velocity of the hip in X and Y, the tangential velocity of the knee in X and Y, and the tangential velocity in the ankle in X and Y. And finally we have the same but for acceleration, which is going to be for the hip, for the knee, and for the ankle. Finally we go back to the report, and we have everything here, all the formulas, all the charts, all the plots obtained from the Excel worksheet, and we have our discussion giving some tips concerning cycling, and also the conclusion. And we concluded that thanks to the acquired results, it was possible to perceive an appropriate position of the thorax because it is more upright than recommended, which gives influence over the way we use our legs to pedal. To continue advancing in a correct execution, it would be more appropriately for both feet to be over the pedal, so that the force exerted by the muscles in the thigh act in better weight than those from the calves, since it seems that the cyclist, in this occasion the one from the video, was not using appropriately his ankle. So having said this, this is it. I hope you enjoyed the video, and everything is here in the report. We're going to be attaching the Word document as well as the worksheet for any further for any further comments about the project. Bye bye.